everybody. This is your video on implicit differentiation for honors calculus. So the next couple weeks after we get back from break, we'll be doing applications of derivatives. One of them is related rates. You can't do related rates unless you can implicitly differentiate. So this video is going to show you how to do that. We'll practice in class a couple times before we get to related rates. So it's important to realize that what we're going to be doing now is we're still going to be doing derivatives and finding rates of change. But the functions that we're doing the derivatives of are not clear. It's not going to be y equals something or f of x equals something. We're going to be finding the derivatives of hidden functions of x. There'll still be a y equals somewhere, but it's not directly stated like what you're used to, y equals. Now, it's called implicit differentiation. So it's important to realize what implicit really means. Implicit is the opposite of explicit. All the functions you've been dealing with pretty much in math, your whole math career so far, are explicit. They're in the form y equals. There is one y, it's on its own, there's an equal sign, and then you have some function of x. So there's some stuff, numbers, only x's on the other side of the equation. And you've been doing the derivative of these. And it's important to realize that when we do the derivative of these, what you've been doing is either writing y prime, or you've also been doing dy dx. So let's do these quick. If I do the derivative of my first equation right here, x cubed plus 1, I'm going to replace y with dy dx. And we're going to talk about why we even do that, because that's going to be basically the premise of this whole video. Then the derivative with respect to x of x cubed is 3x squared. Derivative of 1 is 0. Here, I'm going to replace y with dy dx, the derivative of y with respect to x. And I'll do cosine x. And then for this one here, dy dx equals ho d high minus high d ho all over ho ho. And again, it's very important to realize that you have already been doing this so far by writing dy dx. That's the premise of implicit differentiation. So you've been finding derivatives of things like this, which is dy dx, and the notation here is important and what the notation really means. Dy dx means the derivative of y with respect to x. And another important thing to remember, this is what we've already been doing, is let's take this right here, x cubed plus 1. And let's say I wanted to find the equation of a tangent line, because that's something we've been practicing pretty much this whole year. If I take a cubic x cubed plus 1, it's not perfectly drawn, but it's something like that. And let's say I wanted to find the derivative or the instantaneous rate of change of the function at 1. All I would do is take the derivative, which is here, and then I would plug in 1. I only have to plug in an x value. And that means at 1, the slope of my tangent line is 3. It's hitting at 1 point. And then I got to write the equation of the tangent line by getting a point and using the slope. But the key is you only need to plug an x in, because this is a function for every x, there's one y. So let's talk about x, or implicit now. Take a look at these equations right here. Y is not alone, and usually you won't be able to solve for y to get it alone. So here y is defined implicitly. Before, y was defined explicitly. This is implicit. I still have y's. I mean, there's a hidden function in there, but it's not explicitly stated. It's mixed in with a bunch of x's and y's. So this is what we're going to be doing in this unit here, finding the derivatives of these types of equations. Now, I'm not even going to call these functions, because they're not functions. And Desmos actually has this really cool thing where you can graph implicit functions. So you can type things where x's and y's are mixed together, and they look like this. And this here is definitely not a function because it fails the vertical line test. So if I wanted to do the vertical line test, every vertical line hits the function and more than 1 point, basically 2 points at almost everywhere. So it's not a function. And the thing is, if I want to find the slope of a tangent line at some point, like let's do 1 again, before we found the slope of the tangent line at 1 for a cubic. If I was like, hey, I want to find the slope of a tangent line at 1 here. Well, for this x value 1, there's a y value here and here. So if you took the derivative and plugged 1 in, you're not going to be able to know if you're talking about this point or this point. So you have to plug in not just an x, but an x and a y, because for each x there is more than one y value. And And we are still going to be able to find dy dx for all of these, but we're going to have to use this method called implicit differentiation. And remember, differentiation just means derivative. So the derivative doesn't just depend on x, it depends on x and y. And again, we're comparing that to before, where all we had to do was plug an x in to get the slope of the tangent line. And for each of these x's, the slope is very different. Like here I have a positive slope, and here I have a negative slope. So it's very important that we're plugging in an x and a y. And again, every function that we're going to be dealing with for the next couple of days in this unit, they're not going to look like functions. Again, they fail the vertical line test. But implicit differentiation is going to work because the graphs are usually made up of more than one piece. These pieces are called branches. We're not going to get too in depth into that, but like you can break this into a branch here and a branch here. And then each of those individually is a function. But if you put it all together into this function here, like this is this graph. It's definitely not as a whole a function. So let's talk about how we're actually going to do this. We're going to combine chain rule in order to do this technique. And when you're doing this, you're going to have to remember two things here, the notation and what the notation means. d dx is a command. Like if someone says, hey, do d dx, they're telling you to do the derivative with respect to x. Like whatever the variable down here is, that's what you're doing with respect to. And so far, we've always been doing it with respect to x, and we're still going to be doing it with respect to x, but we're also going to do it with respect to other variables. So it's going to be really important that you realize what this notation means. And then dy dx is different than d dx because dy dx means you've already done the derivative. So we've already done deriv. So again, d dx is a command. It's like, hey, take the derivative with respect to x. dy dx means, all right, I've already done the derivative with respect to x. It's the derivative of y. The thing in the numerator is what you've done the derivative of. The thing in the denominator is what you've done it with respect to. So I'm going to do a couple here with you. The most basic derivatives that you could do to introduce the idea. So let's do d dx of y to the fourth. And you have to focus very carefully here because it's going to seem a little bit weird at first. I'm doing the derivative with respect to x of y to the fourth. And let's hop back over here. When I was here and I did the derivative of y, I replaced it with dy dx. The real reason that we did that is because the derivative of y is just 1, just like the derivative of x is 1. But since I'm doing the derivative with respect to x and y is not x, these variables don't agree, I have to multiply 1 by, or up here, I multiplied 1 by dy dx, which gave me dy dx. So let's do it for y to the fourth. I'm going to do the derivative of y to the fourth, which is just the basic rule here, 4y cubed. But then I have to multiply by dy dx. One way to think of it is like this. Let's rewrite it as d dx of y to the fourth. And I have layers here, so I'm going to do chain rule. Take the derivative of the outside. That would be the 4 and the 3. Then multiply by the derivative of the inside. The derivative of y is dy dx. Just like it was here, the derivative of y was dy dx. All right, let's do another one. Let's do d dx of 3y to the 8th. All right, so if you want to make your inner and outer layers here, you can do that. So y is going to be my inner layer, and the outer layer is going to be this 8. So let's take care of the outer layer first. I'm going to do the derivative, and it's going to be 24, should just be equal sign, 24y to the 7th. And then I'm going to multiply by the derivative of the inside. And the derivative of the inside, well, the derivative of y is dy dx. Another way to think of it, if you don't like the chain rule analogy, is just think anytime there's a y, you're going to put a dy dx after it, if you're doing the derivative with respect to x. So now I want to contrast that with, let's do d dy of y to the fourth. So here I did d dx. Now let's do d dy. Okay, so the derivative of the outside, well, let's do the 4y cubed times, Look, the y matches the y. I'm doing the derivative with respect to y of y. So that'd be the derivative of y with respect to y. dy is just 1. It's irrelevant, so it's just 4y cubed. So if your variables here match, you don't need to do this implicit differentiation. You just take the regular derivative. Just like if I did the derivative with respect to x of x to the 4th, you never thought about doing this implicit before. You just said, oh, okay, this is 4x cubed, because your variables matched. And if you wanted to force implicit differentiation, you technically did the derivative of the outside, so you took the 4 down and subtracted, and then you technically did multiply by the derivative of the inside. The derivative of x with respect to x is dx dx. Dx is just 1, it's irrelevant, so that's why you were able just to say 4x cubed. So again, if your variables match, you don't do implicit differentiation. If your variables do not match, you have to do implicit differentiation. Let's do a full example right here of x squared plus y squared equals 4. And I'm going to want the derivative of this. And if they don't say with respect to, assume it's with respect to x. So what I'm really looking for is dy dx. That's our goal for the next couple of days. Find dy dx. Just like the goal before right here was to find dy dx. I still want that here. And you can see that y is not alone, and it's mixed in with numbers and other variables. So I'm going to do implicit differentiation, and I'm going to do the derivative with respect to x. So I'm actually going to do d dx of this whole thing. So it's a command. It's like, hey, do the derivative with respect to x. The derivative of x squared with respect to x is just 2x. Notice my variables match. I don't need implicit differentiation. Plus, the derivative of y squared with respect to x, my variables don't match, so I'm going to need implicit differentiation. Well, the derivative of y squared is 2y times dy dx. The derivative of a constant is 0. Now, our goal is to get dy dx alone, and it is most definitely not alone right now. So at this point, the calculus is done, and we just have some algebra. So I'm going to bring the 2x to the other side, and then I'm going to divide by 2y. Boop, that cancels, and dy dx is, 2's cancel, negative x over y. So if you wanted the slope of the tangent line at a certain point, you would have to plug in an x and a y. Add this comment right here to your notes so that you remember it. So again, this is the derivative for any xy ordered pair, and you would plug the ordered pairs right into here to get the rate of change at an ordered pair xy. It's not enough just to plug an x in, because again, if I want the derivative at 1, I don't know if I'm talking about the derivative there, like a negative derivative, or the derivative here, which is a positive derivative. So you need to specify not only an x, but also the y. Let's take a look at 2 cases here. These are going to be mixed into the regular. The problems we've done so far were easier. The more advanced ones are going to involve things like this. So if I do the derivative with respect to x of xy, you should immediately look at this and think, I'm multiplying x and y, so I should be doing product rule. So right here, we're going to do product rule while also doing implicit diff. So I have an f and I have a g. So just remember, what I'm going to be doing is f times g prime plus f prime times g. So the derivative, and this is the derivative with respect to x. So let's do the derivative of f. Well, the derivative of x is just 1. The derivative of g, well, the derivative of y with respect to x is dy dx, or 1 times dy dx, plus f prime. Whoa, I just made a mistake. This should just be x because it's f. Whoops. Plus f prime, the derivative of x is 1 times g. So it's just x dy dx plus y. All right, so now let's do it here. You should see 2 things divided and immediately think product or quotient rule. So I have my ho and high. I'm going to do ho, which is just y. D high, derivative of x with respect to x is 1, minus high x. D ho, derivative of y with respect to x is 1 times dy dx, all over ho ho. All right, we'll practice this in class. Have a wonderful break, and I'll see you Monday.